Hello everyone. I was discussing the derivation of the Ehrenfest equations in my last lecture. So taking this forward, we are deriving the first Ehrenfest equation, which arises because of the discontinuity occurring in the Cp versus T graph. Entropy is taken to be a function of pressure and temperature. Pressure and temperature are independent variables. So using this and taking forward and in continuation of my last lecture, I get Cp1 by T plus delta S1 by delta P at constant T dP by dt is equal to Cp2 by T plus delta S2 by delta P at constant T into dP by dt. Here remember, subscript 1 represents the first phase and subscript 2 represents the second phase. Also, dG is equal to VdP minus SdT. So, we have delta S by delta P at constant temperature is equal to minus of delta V by delta T at constant pressure. Using this, we get dP by dt is equal to Cp2 minus Cp1 by T into V alpha 2 minus alpha 1, where alpha is 1 by V delta V by delta T at constant P. So, alpha is the coefficient of volume expansion, and please appreciate that what we have done is we have simply rearranged the first equation on this slide and we have used the definition of alpha in this. We have also used the Maxwell's relation because instead of delta S by delta P, we can now write delta V by delta T, which is nothing but alpha into V. This equation is the first Ehrenfest equation. Now let us derive the second Ehrenfest equation, which represents the discontinuity between alpha and kappa. Using equality of molar volume, small v is equal to V by N in the two phases, we get, because V1 is equal to V2, therefore it follows that dV1 is equal to dV2. Taking V is equal to VTP, where V is a function of temperature and pressure. So, P is equal to capital P by N is the molar pressure at temperature T. We get dV is equal to delta V by delta T at constant P into dt plus delta V by delta P at constant temperature into dP. This implies that delta V by delta T at constant pressure is equal to V alpha and delta V by delta P at constant temperature is equal to minus kappa into V. This would give us dV1 is equal to alpha 1 V dt minus kappa 1 V dP and dV2 is equal to alpha 2 V dt minus kappa 2 V dP. Thus, we finally get dP by dt is equal to alpha 2 minus alpha 1 by kappa 2 minus kappa 1, which is the second Ehrenfest equation representing the second order phase transitions. So, you can appreciate now that the first order phase transition is synonymous with the Clausius-Clapeyron equation and the second order phase transition is synonymous with the Ehrenfest equations. Ehrenfest equations are 2 in number and Clausius-Clapeyron equation is 1 in number. So this is as far as the thermodynamic potential is concerned, and this concludes my discussion on the thermodynamic potentials. Next, I move on to a very important phenomena called the adiabatic demagnetization. I will discuss what is meant by this, what is the experimental setup to see actually the phenomena of adiabatic demagnetization, what is the principle behind this particular phenomena, what is the theory behind this phenomena, what are the results of adiabatic demagnetization, and why is it useful. So first of all, adiabatic demagnetization is a method to obtain low temperatures. Always remember this. If you remember, in my previous lectures, I have also discussed the Joule-Thomson experiment, which also was an experiment to show that low temperatures can be achieved even if you start with high temperatures if you pass the gas through a porous plug. Not any gas, a compressed gas. Now let me move on to the adiabatic demagnetization. In 1926, two scientists, Debye and Guiac, showed theoretically that the temperatures considerably below 1 Kelvin could be obtained by the process known as adiabatic demagnetization of paramagnetic salts. What are paramagnetic salts? The salts whose susceptibility is small but positive. This is very important. Another scientist, Haas, in 1994 was able to produce a very low temperature 0.002 Kelvin using a double sulfate of potassium and aluminium. Another group of scientists, Clark, Stenland and Gotter, used powder mixed crystal of chromium alum and aluminium alum and achieved a low temperature of 0.0014 Kelvin. These scientists also used the method of adiabatic demagnetization. Now let me discuss the principle behind this particular phenomena, adiabatic demagnetization. If you listen or if you just understand the topic itself, the meaning is clear, the principle is clear. But let me discuss this in detail. First of all, adiabatic demagnetization is a process of cooling. The principle is that a paramagnetic salt heats up when placed in a magnetic field and cools down when removed from the magnetic field under adiabatic conditions. This is very, very important. That magnetic field should be switched off under adiabatic conditions. What happens when you expose a substance to magnetic field? The process of magnetizing a substance involves doing work on the substance which will slightly heat the substance. The work done in aligning the elementary magnets, that is, the atoms of the substance in the field direction, is stored in the substance in the form of magnetic energy. If such a substance is demagnetized adiabatically, it has to do work, and the energy required for this is drawn from within. This results in the cooling of the substance. So this is the principle, that a substance is first of all magnetized and then demagnetized adiabatically. But this does not happen for every substance. The substance has to be paramagnetic in nature. Hence, what we can conclude is this, that when a paramagnetic material is placed in a magnetizing field H, its elementary magnetic dipoles align parallel to to the direction of the field. The magnetic moment produced per unit volume because of the exposure of the substance to the magnetic field is called the intensity of magnetization and is represented by the symbol I. According to Curie's law, this intensity is directly proportional to the magnetizing field. That is, more the magnetizing field, more would be the intensity of magnetization. Further, the intensity of the magnetization is inversely proportional to the temperature T of the paramagnetic substance. So, more the temperature, less would be I. By measuring the magnetic susceptibility of the substance using a mutual inductance coil before and after the demagnetization, the final temperature is computed. So, we are not calculating or finding out the temperatures by simple thermometers. We are using a mutual inductance coil which would measure the susceptibility. Susceptibility is inversely proportional to temperature and therefore temperature can be found out before magnetization and after demagnetization. Using this phenomena, temperatures in the range of 0.001 Kelvin were attained by many researchers. Now let me discuss the experimental setup. The paramagnetic salt which is taken is gadolinium sulfate. It is suspended in a vessel surrounded by liquid helium taken in the Dewar flask D1. The liquid helium taken in the Dewar flask D is boiled under reduced pressure. So, this is the experimental setup. You can appreciate on the left and the right you can see the electromagnetic poles. You have strong electromagnet. This electromagnet helps in magnetizing the paramagnetic salt. The paramagnetic salt is suspended in the inner glass chamber. The inner glass chamber is surrounded by two Dewar flasks, U-shaped Dewar flasks. These are special flasks, double walled flasks. In one flask we have liquid helium and in the other we have liquid hydrogen. We also have an arrangement of the U-tube to connect to the vacuum pump for evacuating it and exposing it to adiabatic conditions. It is surrounded by liquid hydrogen taken in the Dewar flask D2. The whole arrangement is kept between the poles of a strong electromagnet. Initially, the salt is in contact with the helium gas. That is, the temperature of the salt is that of the temperature of helium, which is 4.2 Kelvin. A magnetic field of the order of 30,000 Gauss is applied. So, you can appreciate a very strong magnetic field is applied. Once the magnetic field is switched on, the specimen gets magnetized. Now, what happens because of magnetization? Heat is generated into the sample. This heat generated in the sample during the process is removed by introducing the hydrogen gas into the chamber A and then pumping it out using a high vacuum pump so that the specimen gets thermally isolated. Now, why is this important? Because we have to do the experiment under adiabatic conditions. That is, the specimen does not gain heat nor does it lose heat. So, we have put it under vacuum conditions. The specimen attains the temperature of the liquid helium which is being pumped so that it boils under reduced pressure. This temperature is in the range of 1 Kelvin. It means initially gadolinium sulfate is at a temperature of 1 Kelvin when it is exposed to the magnetic field. When the magnetic field is switched off under adiabatic conditions, the adiabatic demagnetization of the specimen takes place, which causes a reduction in the temperature of the gadolinium sulfate. Initially, the temperature was 1 Kelvin. So, if the temperature now falls, it should be much less than 1 Kelvin. The temperature of the specimen is determined by fitting a coaxial solenoid coil around the tube A and measuring the self-inductance and hence the susceptibility of the substance at the beginning and the end of the experiment. This is very important because the whole outcome of the experiment depends upon the temperature measurement. Then the temperature T is given by Curie's law. Chi is equal to C by T. Chi is the susceptibility, C is the Curie constant and T is the temperature. This entire phenomena is also called the magnetocaloric effect. So again I am showing you the setup to give you a further view of the setup, that we have electromagnets, we have two Dewar flasks, we have a paramagnetic substance, we have a vacuum pump, we have solenoid coils. Now let me discuss the theory behind the experiment. We apply the first law of thermodynamics to the magnetic substance. For a magnetic system, we have an additional conjugate pair B, M, where B is the magnetic field and M is the magnetization produced because of this magnetic field. The magnetic work done on the system by the applied field B in increasing the magnetization of the system from M to M plus dm is given by dW equal to minus B dot dm. Now remember, we have work done in simple thermodynamical system as P dV. It means we are replacing P by minus B and V by M. Here we have used the negative sign for the work done on the system and the fact that the change in magnetization dm is along the magnetic field B. Using the first law of thermodynamics, we have dq is equal to du plus p dv. The second law says that dq is tds. So we have now tds is equal to du plus p dv. When a paramagnetic salt is placed in a magnetic field of flux density B, I increases. This I is proportional to B, the magnetic field, and is inversely proportional to T, the temperature of the paramagnetic substance. So we can write I is equal to C into B by T, where C is nothing but the Curie's constant. This is also called the Curie's law. If V is the volume of 1 mole, then the intensity of magnetization I becomes M equal to IV. So we can write M is equal to C into B by T into V. The work done on the salt is B into Di. So the TDS equation will now become TDS is equal to du plus PdV minus BDI. Since the process is carried out at constant pressure, we have dV equal to 0 or TdS is equal to du minus bdi. Comparing 2 and 3, we get minus B corresponds to P and M corresponds to V in a magnetic system. Maxwell's relation gives us delta T by delta P at constant entropy is equal to delta V by delta S at constant pressure. Now you can see we don't have a negative sign here because the variables are taken in a clockwise direction. The first law can be written as dq is equal to du plus pdv minus bdm. du minus bdm, where we have used the fact that there is negligible or no change in volume of a solid specimen during the process. So if we replace P by minus B and V by M, we get minus of delta T by delta B at constant S is equal to delta M by delta S at constant B. So this will give me minus of delta M by delta T at constant B into delta T by delta S at constant B, or delta T by delta B at constant S is equal to minus delta M by delta T at constant B divided by delta S by delta T at constant B. Here we have simply taken one term of the numerator into the denominator. Further, delta S is nothing but delta Q by T. Thus, we have delta S by delta T is equal to 1 by T delta Q by delta T at constant B, or delta S by delta T is equal to M into Cb by T, where M is the mass of the specimen and Cb is the specific heat at constant magnetic field. We have used the same notations as we had done in the case for specific heats at constant volume and constant pressure, that is for Cv and Cb. Taking M equal to 1, we get delta T by delta B at constant S is equal to minus of delta M by delta T at constant B by Cb by T. So we get finally delta T by delta B at constant S is equal to minus T by Cb delta M by delta T at B, or delta T is equal to minus T by Cb delta M by delta T at constant B dB. This gives the fall in temperature due to adiabatic demagnetization. Now why are we saying it is a fall? Because as you can see, already a negative sign is appearing in equation 6th. Now because we have the case of demagnetization, so delta B also has to be negative. Further, we are taking delta M by delta T for a paramagnetic salt, which is again negative. So we get delta T as negative. The following conclusions can be drawn from the equation. The temperature of the paramagnetic solid decreases as the magnetizing field is reduced. It is indicated by negative sign of delta T. Greater be the initial field, lower be the initial temperature, greater would be the temperature fall delta T. It is to be noted here that Cb is the Curie's constant per mole. If 1 gram of paramagnetic substance is taken, then Cb would stand for Curie constant per gram. This means that adiabatic demagnetization is an important phenomena through which we can attain low temperatures, but you can appreciate the fact that we start also at a very low temperature. We started at temperatures of the order of 1 Kelvin, and using that we could attain a temperature less than 1 Kelvin. An extension of adiabatic demagnetization process is the nuclear adiabatic demagnetization experiment. This experiment helps to attain a much lower temperature than would have been possible had only adiabatic demagnetization process been used. If we do it for a nuclear system, then we can attain a much lower temperature. Why? Because this technique depends upon the nuclear dipole's alignment, which is 1000 times smaller compared to atoms. With this method's help, the temperature of the ordered nuclei can be reduced to 0.000016 degrees. So you can appreciate how effective the nuclear adiabatic demagnetization experiment is. Now let me discuss one question to understand the concept of adiabatic demagnetization, how we can use this to find out the fall in temperature. Calculate the cooling produced by adiabatic demagnetization of a paramagnetic salt as the field is reduced from 1000 Oersted to 0 at initial temperature of 2 Kelvin. Curie constant per gram mole per cc is given 0.042 and the value of Cb is also given, which is 0.42 joules gram minus 1 degree minus 1. Now we know, according to the formula we have just derived, that the fall in temperature, we always say the fall in temperature because we know it is the fall in temperature. Delta T is equal to minus V by 2 Cb T average into B. Here we are given the field as 10,000 Oersteds. The value of Cb is given to be 0.42 gram minus 1 Kelvin minus 1. If I change this, then I get 0.42 into 10 to the power 7 ergs gram minus 1 Kelvin minus 1. It is sometimes important to look at the units, it is always important to look at the units and change the units into one particular nomenclature, either the SI units or the CGS units. Curie constant is also given in the SI system. So delta T will be equal to 0.042 erg Kelvin gram minus 1 Oersted minus 2 divided by 2 into 0.42 into 10 to the power 7 into 2 Kelvin into 10,000 Oersted square. So we get delta T as minus 0.25 Kelvin. So you can appreciate how to calculate the temperature change. Likewise, you can practice on this particular question also. Here again we are supposed to find out the fall in temperature where magnetic field is given as 8400 Oersted, T is given as 3 Kelvin, the value of Curie's constant is given and Cb is also given. So I hope you have understood the concept of adiabatic demagnetization. It is an important topic in thermal physics and has various applications in attaining low temperatures. Thank you so much.